Well, hello there class, this is Mr. Matthijs. The purpose of this video is to just demonstrate the solutions to the Section 2 homework assignment from Chapter 11. This was the assignment focusing on games that are not strictly determined. Non-strictly determined games, finding the optimal strategies and the values of games like that. So it's going to be a bit of a longer video, just going through all the questions, but you can use this to check your work, check out questions that you were stumped on. You can kind of skip through the video to just see what you need to see. Hope this is useful for you. Okay. So the first question had 4 parts. It was kind of all just repeating the same skill to just hammer it down. So we've got a game matrix, and we need to determine the optimal strategies for the row player and the column player, and then to find the value of the game. So the row player is going to start with an arbitrary strategy, R and 1 minus R, as the breakdown among like what percent are they going to play their first option and what percent are they going to play their second option, those 2 percents adding up to 100%. And then we'll just compare those against both of the possible columns, doing that with multiplication. So we have R times -1 is -R, plus 1 minus R times +1. That gives us -R plus 1 minus R, or -2R plus 1. And then if we take our arbitrary row strategy and multiply it by the second column, 1 -1, that gives us R times 1 is R, plus 1 minus R times -1 is R minus 1 plus R, or 2R minus 1. And then we'll just set these two equal to each other, and that'll give us the optimal value for R. So -2R plus 1 equals 2R minus 1. We can add 2R to both sides and add 1 to both sides. Okay, that'll give us 2 equals 4R. So R equals 2 over 4, or 1/2. So it looks like for the row player optimal strategy is to do 50-50. Half the time choose their first option, and half the time choose their second option. Fantastic. Okay, so then we'll look at the we'll look at the column player. So I'm just going to bring this down and make some more room. So now we're looking at the column player. The column player is going to start with some arbitrary strategy where they play C and 1 minus C, for the same logic of why the row player plays R and 1 minus R. And we'll just compare that to the 2 possible rows. So if they play that strategy against the first row, it's a C, they'll get -1 times C is -C, and then plus 1 times 1 minus C. So they'll have -C plus 1 minus C. That's -2C plus 1. And then if they play that strategy against the second row, 1 -1 against C and 1 minus C, oops, 1 minus C, that will be 1 times C is C, plus a -1 times 1 minus C gives us C minus 1 plus C, or 2C minus 1. So again, we'll set these equal to each other to find the optimal value for C. So we got 2C minus 1 equals -2C plus 1. We can add 2C to both sides and add 1 to both sides. That gives us 4c equals 2. So it looks like C is also going to be 2/4 or 1/2. So C's optimal strategy is also going to be 50-50, playing each of their choices half of the time. Okay, so let's look back to the question we're trying to answer. Determine the optimal strategies for both the row player and the column player and find the value of the game. So I'll just make a little bit more room here. Bring our game down with us. So the optimal strategies, right? The row player wants to play 1/2, 1/2. The column player wants to also play 1/2, 1/2. I guess I should have written this as a column. Sorry. So the column player should be 1/2, 1/2. And then recall that the value of the game, the value can be found by doing our row times our game times our column. Where this is our game here. So I'm just going to do that in my calculator. I'm just going to do some matrix calculations in my calculator. I'm going to put in R for matrix A in my calculator. It'll be a 1/2 matrix with entries 0.5 and 0.5. Matrix B, I'll make that a 2/2 matrix with our game matrix G, and that's -1, 1, 1, -1. And then matrix C is going to be a 2 rows by 1 column matrix with entries 0.5, 0.5. So that what I'm really doing in my calculator is A times B times C. And when I do that, A times B times C, I get a value of 0. So it looks like if both players play their optimal strategies, the value of the game is 0. Okay, so that's part A of number 1. Okay, let's go on to part B of number 1. This one is going to be very similar to what we just did. We're going to find the strategies, optimal strategies for the row player and the column player, and then use those to find the value. So again, the row player is going to play some arbitrary strategy R and 1 minus R, and they're going to play that against both columns and see what happens. So if they play that against the first column, they get R times 1 is R plus 1 minus R times -4. That gives us R plus -4 plus 4R. So we have 5R minus 4. And then when they play that arbitrary row strategy against the second column of -1, 0, then they get R times -1 is -R. And 1 minus R times 0 is 0. So just -R. So then we'll just set these two results equal to each other. 5R minus 4 equals -R. We can add R to both sides and add 4 to both sides. That'll give us 6R equals 4. So R equals 4/6 or 2/3. So it looks like our row strategy should be 2/3 for the first option and 1/3 for the second option. Okay, now we will look at the column player for the same game. The column player. So the column player is going to play against both rows. And they're going to play an arbitrary strategy. Negative 1. So they're going to play an arbitrary strategy of C and 1 minus C against both rows and find out what value for C makes that the best strategy. So they play that against the first row. We get 1 times C is C, and negative 1 times 1 minus C. That gives us C minus 1 plus C, or 2C minus 1. And then they play that same column strategy against the second row, negative 4, 0, and C, 1 minus C. That gives us negative 4C plus 0, or negative 4C. So then we are going to set these two results equal to each other. 2C minus 1 equals negative 4C. So I'll add 1 to both sides and add 4C to both sides. That'll give us 6C equals 1. So C equals 1/6. So that means that the column strategy should be 1/6 for the first option and 5/6 for the second option. So that's the optimal strategy for the column player. And then the last question we're trying to answer is the value of the game. All right, and there's our game matrix. So remember that the value is just going to equal the row times the game times the column. So in this case, that's our 2/3, 1/3 times the game 1, negative 1, negative 4, 0 times the column 1/6 and 5/6. And we can just use our calculator to do this for us and find what the value is. So I'm going to go to my calculator. I'm going to edit my matrices. I'm going to put in my row into matrix A, 2/3, 1/3. I'm going to put in my game into matrix B, 1, negative 1, negative 4, 0. And I'm going to put in my column into matrix C, 1/6, 5/6. And then I'll just multiply them. So this is A times B times C in the calculator. And when I do that, here's what I get. I get negative 2/3. I actually got negative 0.666666667, but that's equal to the fraction negative 2/3. So the value of the game is negative 2/3 for the row player. Remember that values are always relative to the row player. So in the long run, the row player will lose 2/3 of a point, and the column player will gain 2/3 of the point in the long run. Okay, moving on to part C. Same type of question, same process. So we'll start with our arbitrary row strategy. R1 minus R times the first column, 3, 2. That'll give us 3R plus 2 minus 2R, or R plus 2. And then we'll compare our row strategy against the second column, negative 2, 4. That'll give us negative 2R plus 4 minus 4R, or negative 6R plus 4. So then we'll set our two results equal to each other, and that will give us R plus 2 equals negative 6R plus 4. So let's add 6r to both sides and subtract 2 from both sides. That'll give us 7r equals 2, or r equals 2/7. So our row matrix is 2/7 and 5/7. So that's the optimal strategy for the row player, is to play their first option 2/7 of the time and their second option 5/7 of the time. Okay, so now we need to discuss the column player. So I'll bring this down, make some more room. We're going to compare the two row choices, starting with the first row, against an arbitrary column strategy of C and 1 minus C, and find what value for C makes this the optimal strategy. So we've got 3 times C is 3C, and then -2 times 1 minus C gives us -2 and positive 2C. So that'll give us 5C minus 2. Then we'll compare that same column strategy against the second row, 2, 4, against C and 1 minus C. So that'll give us 2 times C plus 4 times 1 minus C. So that'll give us 4 and -4C. 2C minus 4C is -2C plus R4. So then we set our two results equal to each other to see what value of C we get. 5C minus 2 equals -2C plus 4. So let's add 2C to both sides and add 2 to both sides. That'll give us 7C equals 6. So C equals 6/7. So that means our column strategy is 6/7 for the first option and 1/7 for the second option. So those are our optimal strategies. Our optimal row is 2/7, 5/7. Our optimal column is 6/7, 1/7. So then we just need to use those and our game to find the value of the game. So again, the value is going to be row times game times column. That's our 2/7, 5/7 times our game, 3, -2, 2, 4, times our column, 6/7, 1/7. And again, I'll go back to my handy dandy calculator. For A, we have our row 2/7, 5/7. For B, we have our game 3, -2, 2, 4. And for C, we have our column 6/7 and 1/7. Okay, so I've just put these in my calculator as A, B, and C. So then I just need to call A times B times C. And this is what I get as my value. 2.2857, blah, blah, blah. Let's see if I can turn that into a fraction. I can. The fraction is 16/7, or 2 2/7. So that's the value of the game, which represents a win for the row player because it is a positive value. So hooray for the row player. Okay, this is the last part of question 1, which is D, and we're just going to do the same thing. Start with finding the optimal strategy for the row player, then the column player, then the value of the game. So, for the row player is playing an arbitrary strategy of R and 1 minus R against the first column of -3, 1. That gives us R times -3 plus 1 minus r, or negative 2 minus r. And then they play that strategy again against the second column, 2, negative 4. That gives us 2r minus 4 plus 4r, or 6r minus 4. So we'll set these equal to each other to find the value for r that optimizes the game for the row player. So let's add r to both sides, and we'll add 4 to both sides. That gives us 7r equals 2, or r equals 2/7. So that gives us our row strategy. R is 2/7, 1 minus r is 5/7. I feel like I'm getting deja vu. That was the same answer we got last time. Okay, so there's our optimal strategy for the row player, 2/7, 5/7. Now we'll look at the column player. So I'll drag our game down and make some more room. Our column player is going to play against the two rows using an arbitrary strategy of c and 1 minus c. So doing that, we get negative 3 times c is negative 3c, plus 2 minus 2c, or negative 5c plus 2. And then we play against the second row, 1, negative 4, against our arbitrary column strategy. Gives us 1 times c minus 4 plus 4c, or 5c minus 4. Then we'll set these equal to each other and see what c equals. Negative 5c plus 2 equals 5c minus 4. Add 5c to both sides. Add 4 to both sides. That gives us 6 equals 10c. So c equals 6/10, or 3/5. So that means our column strategy should be 3/5 for the first option and 2/5 for the second option. So that's our optimal strategy, 3/5 and 2/5. Okay, so that just leaves the finding of the value of the game, right? So one last time, the value equals the row times the game times the column. Our row, if I recall, was 2/7, 5/7. Our game here, negative 3, 2, 1, negative 4. And our column, 3/5, 2/5. So I'm just going to put these into my calculator as A, B, and C and multiply them, and that will give us the value. So matrix A, 2/7, 5/7. Matrix B, negative 3, 2, 1, negative 4. And matrix C, 3/5. And 2/5. And then I'll just do A times B times C. And I get a value of negative 1. So that is the value of the game, negative 1. So it's a loss for the row player. Both players playing their optimal strategy. Okay, so that's the 4 parts of number 1. Moving on to number 2. Here we're given a game matrix and we're given a particular row and column strategy, right? So we're tasked to find the expected payoff. Okay. So here again, our value or our expectation, I guess I'll use E. We can't say that it's the value of the game because we don't know if this is the optimal strategy, but the payoff for this strategy would again be R times G times C. So I just need to go back to my handy dandy calculator and put in those matrices and multiply them. So I'll put our row into matrix A, and that is 2/3, 1/3. Then I'll put in our game into matrix B, and that looks like the same matrix we just had in number 1 part D, which is -3, 2, 1, -4. And then I'll put in our column matrix in for C, which looks like a strategy of 1/4 and 3/4. So in my calculator, what I'm doing is A times B times C, and that is equal to, as a decimal, -0.41666 ... As a fraction, that is -5/12. Okay, 2B is very similar. We're given a game matrix, a row matrix, and a column matrix. We want to find the expected payoff. So again, P equals row times game times column. So that's exactly what we'll do in our calculator. A will take our row matrix of 1/3, 2/3. B will take our game matrix, -1, 1, 1, -1. And C will take our column matrix of 2/3, 1/3. And then in our calculator, then we have A times B times C, which in this case is a value of 0.1111 ... which as a fraction is 1/9, I believe. So that's the value of the game, 1/9, according to this strategy. Okay, on to number 3. 2 players play a game which involves holding out 1 or 2 fingers simultaneously. If the sum of the fingers is even, player 2 pays player 1 the sum of the fingers. If the sum of the fingers is odd, player 1 pays player 2 the sum of the fingers. So first we need to write a payoff matrix for player 1. Okay, so for player 1 tells us that player 1 is going to be the row player, because these things are always relative to the row player. So if we want to know about player 1, we'll make player 1 the row player. So that means player 2 is the column player. They both have 2 choices, 1 finger or 2 fingers. And those choices combine to have values that we will put in this matrix. So if they both play 1 finger, then the sum of the fingers is 2. If the sum of the fingers is even, player 2 pays player 1 the sum of the fingers. So since it's 2, that's an even, so that's a positive result for player 1. What about 2 fingers for player 1 and 1 finger for player 2? That would be a sum of 3, which is an odd number. If the sum of the fingers is odd, player 1 pays player 2. So that would be a negative result if the sum is 3. So if he plays 2 and the other player plays 1, or if it's 1 against 2, either way, that's going to be a negative result of 3 for our player 1, our row player. And then the last possibility is they both played 2 fingers, so that would be a sum of 4, 4 is even, so that's a positive result for our row player. So there's our payoff matrix. 2, -3, -3, and 4. And I've got a hunch that we're going to need that. So I'm just going to copy it so that we can paste it onto our next slide. Because now we're being asked to find the optimal strategies and the value of the game. So I'll paste our game matrix so that we can see it. So let's find the optimal strategies. The row player will start with a arbitrary strategy of R and 1 minus R, and we'll compare that to the two columns. R times 2 is 2R, and 1 minus R times -3 is -3 plus 3R, or 5R minus 3. And then if we play against the second column, -3, 4, that gives us R times -3 is -3R. 1 minus R times 4 is 4 minus 4R, or -7R plus 4. So we'll go ahead and set those equal to each other. 5R minus 3 equals -7R plus 4. We'll add 3 to both sides and add 7R to both sides. That gives us 12R equals 7. So R is 7/12. That means our row strategy should be 7/12 of the time they should play the first option, 1 finger, and 5/12 of the time they should play the second option, 2 fingers. So that's our optimal strategy for the row player, player 1. Now, what about the column player? Let's see, can I bring this down here? Okay. So now we're going to find the optimal strategy for the column player by comparing it against the two possible rows. So we've got 2, -3 against C1 minus C. That gives us 2 times C. And -3 times 1 minus C is -3 plus 3C, or 5C minus 3. And then we'll play our arbitrary column strategy against the second row. -3, 4 against C1 minus C. That gives us -3C plus 4 minus 4C, or -7C plus 4. So we'll set those equal to each other and see what value of C optimizes the strategy. 5C minus 3 equals -7C plus 4. This looks pretty familiar here. And I'm just going to solve the equation here. 12C equals 7. So C equals 7/12. So the column player's optimal strategy is to play 1 finger 7/12 of the time and 2 finger 5/12 of the time, which is the same strategy as the row player, I believe. 7/12, 5/12. So both players have the same optimal strategy. And the last thing we need to find out is what is the value of the game, assuming that they both play the optimal strategy. So I'll bring our game down so that we can see it. Right, so our value is going to be row times game times column. That's our 7/12, 5/12. times the game, 2, -3, -3, 4, times the column, 7/12, 5/12, right? So then I'll just put those into our calculator, and that will tell us what the value of the game is. So our row is going to go into matrix A, 7/12, 5/12. Our game is going to go into matrix B, 2, -3, -3, 4. And our column will go into matrix C, 7/12, 5/12. And then, just like magic, A times B times C equals, as a fraction, -1/12. So, looks like a slightly losing game for player 1 in the long run. Okay. Last but not least, we have question number 4. Okay, question number 4 is a word problem. Very timely. In December 1995, President Clinton ordered the first of 20,000 U.S. troops to be sent into Herzegovina as a peacekeeping force. Unfortunately, the heavy fog made visibility very poor at the Tuzla airfield, and at the same time increased the threat of sniper attacks from the Serbian forces. U.S. Air Force Colonel Neil Patton and Lieutenant Colonel Sid Kooiman, the advanced specialists, had two choices: either to send in the troops by air, with the difficulties already described, or by road, thus exposing the troops to ambush by the Serbian forces. The Serbian army, with its limited resources, had a choice of deploying its forces near the airport or along the road route. Okay, so this kind of sums up our choices. So if we're going to write off a payoff matrix for the game, we've got the US versus Serbia, and they both have the same options, either air or road. The US can either choose to go in by air or by road, and Serbia can either choose to defend by air or by road. So those are the choices for the two players. Now, if the US lands its troop on the airfield in the fog while the Serbs are concentrating on the road route, the payoff for the US is 20 points. So if the US goes by air and the Serbians defend by road, then that's a 20-point value for the US. If the US lands its troops on the airfield and the Serbians are hiding in the fog, if they're defending the airfield, the US wins only 5 points. So air against air, 5 points. On the other hand, if the US transports its troops by road and avoids the Serbs because they're defending in the air, the payoff is 35 points. But if the US meets Serb resistance on the road, it loses 50 points. So if they go by road and the Serbians are defending the road, then they will lose 50 points. So that's the payoff matrix for the game. It's a game with US and Serbia both having the same two options, and these are the values of their combined possible choices. Okay, part B. If you were the Air Force Colonel Neil Patton's advisor, what advice would you give him? So in other words, we need to find the optimal strategy for the US, who is the row player, right? Well, that's what we've been doing this entire time, so let's just do it again. We're going to decide some arbitrary strategy for the US and see how it compares against the two possible column strategies for Serbia. R times 5 is 5R. 1 minus R times 35 is 35 minus 35r, or negative 35r plus, negative 30r plus 35. And then against the second column, 20 and negative 50. We have 20r minus 50 plus 50r, or 70r minus 50. Okay, so we'll set those two equal to each other and see what value we get. Negative 30r plus 35 equals 70r minus 50. So we'll add 30r to both sides, and we'll add 50 to both sides. That'll give us 85 equals 100r, or r equals 85 over 100. Or in other words, r equals 0.85, 0.85. So it looks like the row strategy for the US should be 0.85, 0.15. Now, let's also think about what the Serbian strategy might be. All right, so I'm going to try to copy over this. Here we go. All right, so I'm going to bring down our game matrix. There we go. So what strategy might the Serbs consider? Well, their strategy is going to look generally like this, C1 minus C. So let's see how that compares against the two possible row options. 5 and 20 against C1 minus C. That gives us 5C plus 20 minus 20C, or negative 15C plus 20. And against the second row, 35 and negative 50 against C1 minus C. That'll give us 35C minus 50 plus 50C, or 85C minus 50. Okay, so we'll set those equal to each other to find the optimal value for C, the column player, representing Serbia. Okay, so negative 15C plus 20 equals 85C minus 50. We'll add 15C to both sides, and we'll add 50 to both sides. That'll give us 70 equals 100C. So C equals 70 over 100, or 0.7, 70%. So it looks like the Serb strategy should be 70%, 30%. Okay, so those are our optimal strategies, right? Our optimal strategy for the US, 85% by air and 15% by road. And for the Serbs, 70% by air and 30% by road. And then the last thing we can do is to find the value of this game if both countries play their optimal strategy. So again, there's our game matrix, right? And our value of the game. The value of our game is going to be row times game times column. So that'll be our 0.85.15 times this game matrix 5, 20, 35, -50 times our column matrix 0.7.3. So I'll just use my calculator to do this computation, putting in our row into matrix A, 0.85.15, putting in our game into matrix B, 5, 20, 35, -50, and putting in our column into matrix C, 0.7.3. ABC, just like magic, we get a value of 9.5. So what does that tell us? What does that tell us? Remember, the question we're trying to answer is if you were the colonel's advisor, what advice would you give him? Well, our advice should be send 85% of our troops by air and 15% by road. Against the optimal strategy for the Serbs, it will be a victory because we have a positive outcome. So no matter what, it'll be a victory for the United States. I guess if you wanted to, we know that it's 20,000 troops, right? So if you want it to be even more specific, 20,000 times 0.85, that would be 17,000 by air, and then 20,000 times 0.15 should be 3,000, so 3,000 troops by road. That's the optimal strategy for the United States, which, even against the best strategy for Serbia, will represent a victory for the United States. Okay, so that's the homework. I hope that this was a helpful video for you. If you have any questions, don't hesitate to send me an email. Okay, have a good one. Bye.